Hello, welcome to week 8 of the course on big data. So, in this week, we will start to look at two of the other technologies that form a very good alternative in the open source domain for processing streaming applications. So, we took a look in the previous week about the streaming context itself and how it's actually different from the batch processing context. Specifically, there were two pieces of software that were critical, which if we adopt frameworks which are readily available, then it makes our life much easier when we start looking at building our own streaming applications. The first is the persistent store software, or also called as a message service, message bus, and so on. Those are all different terms for it. The other is the stream processing software. Sometimes the stream processing software is also called as the event processing software or complex event processing software. So all of those are equivalent terminologies. So in this week, we will take a look at Kafka, which is part of the Apache Software Foundation. And also we will take a look at the streaming module within Apache Spark. So let's start with introduction into Kafka. So Apache Kafka actually started as a project within LinkedIn. This was quite some time ago, more than a decade ago. But the crux of what they were trying to do at that time was to build a very simple message bus, which allowed for scalably delivering events to various consumers without having to be bottlenecked on tracking where the different consumer is in terms of their consumption, as well as without having to have any kind of backwards pressure on the producer. So the fundamental design of Kafka was actually quite simplistic, but it took a lot of thought. It took a lot of experimentation, a lot of real world experience of having scaled up the event delivery to the scale of LinkedIn as the company was growing. So very soon, the creators realized that this was actually much larger than what they initially set out to achieve, and then it became an open source project. And the moment it became open source and became part of the Apache Software Foundation, its use just skyrocketed. So to put things in context, prior to Kafka coming into the play, there were actually a few other open source message bus, message queue kind of technologies. RabbitMQ, ZeroMQ, and so on. And then there were also proprietary technologies from the likes of companies like TIBCO. But then what happened was the open source technologies for message queues were great at small scale applications, which are typically web applications. And they didn't really have the scale characteristics that, for instance, Hadoop had, right? Which meant that you couldn't just put a bunch of commodities hardware and then build a massive cluster of a very large message bus, which is able to cater to millions of events happening on a regular basis. That wasn't possible with those open source technologies at that time. And then, of course, the proprietary versions were significantly more expensive, and it was more a black box. At the same time as message bus technologies evolved, there was also this movement towards service-oriented architectures on the software side. What service-oriented architectures really mean was that you actually had each software doing or publishing a particular service, and then the service was actually published in a actually central enterprise bus, and that enterprise bus allowed anybody anywhere sitting on the bus to come in and consume a service and discover what services existed and so on. Very soon, the motivation for creating more software around using the SOA concept, the service-oriented architecture concept, actually dovetailed very well to the message bus developments in the message bus technology space. So that's how the two kind of grew organically. But then once Hadoop came into picture, once Kafka was invented, around the same time is when cloud native started to become a big concept. We took a look at cloud native in week 1. But then at that time, the software architectures also started to get even more nuanced. So from service oriented, the kind of software that was getting built for the cloud became microservices oriented. So again, the word microservices refers to the fact that in the service oriented architecture, the services were becoming large and unwieldy because they were doing a lot of different things, albeit all of those things were related to a business context. And because they were doing these large unwieldy things, the problem of integrating all these different services and making sure that the data that gets exchanged between the services were homogenized and consistent, etc., became a pretty complex and daunting problem that the service bus or the message bus had to solve for. And slowly those kinds of architectures became monolithic. Whereas with the world of big data, with the world of cloud native, when microservices architectures became popular, it became even more interesting and relevant to think about services as doing exactly one thing and doing it really well, and being able to do it in a way that allows it to scale by having multiple copies of those microservices. So the moment you do that, these microservices have to exchange data even more compared to the services which are like monolithic, right? Because in a monolithic system, rather in a relatively more monolithic system, you could actually have data and exchange, rather data and messages be within the software, right? So that all the different things that need to happen sequentially can happen. And then once you're completely done, and then you can actually publish the final output. Whereas in the microservices based architecture, where the microservice is doing exactly one thing, in order for two microservices to talk to each other and exchange information, they have to, start thinking about how do I get my output to it, and how do I get its input and so on. So that actually, went very well hand in hand with a scalable event store like Kafka, right? So kind of each fed into the other. The popularity of Kafka allowed for more microservices based implementations to happen in the world, and vice versa. Like the microservices based architectures became feasible because of Kafka, because of the low cost, very simple to understand operating model that Kafka brought to the table. So that's the context. Let's dive deeper into Kafka. So Kafka is actually, again, an example of a message bus. Specifically, it is designed to actually have a distributed architecture, which is massively parallel, allows for multiple different consumers and producers to operate at the same time, etc. So it's a very similar kind of description to what we talked about in PubSub. Because Kafka is open source and it's a software, you have to manage your own Kafka typically in your environment. With public cloud, there are managed Kafka options available, so that it kind of simulates it provides a PaaS interface, which is a platform as a service interface, but kind of simulates a serverless interface as well in some cases, where you don't need to actually specify machine sizes beyond just initial configurations. But yeah, all said and done, the advantage of having actually Kafka is it's open source. You can actually control the environment yourself, and it's very conducive for, like I said, software shops, right, which write their own software. One of the biggest advantages of actually having Kafka being designed the way it is that multiple different consumers can actually keep track of where they are in terms of consumption. And this is slightly different from how, for instance, PubSub does it, and very different from how the open source earlier open message queue technologies like 0MQ and RabbitMQ do it. So specifically, the consumers keep track of where they are, and as and when they want to consume, they just consume and then update that track. I mean, basically those tracks are called offsets. We'll talk about that in the next couple of slides. But the advantage here is that Kafka by itself is actually not tracking anything, right? All the Kafka is saying is, I'm going to make a bunch of messages available to anybody who wants to consume. And these are messages produced by producer. And what's more, I'm going to make some nifty optimizations, meaning I'm going to make some, fundamental practical design choices, which allow for very, very fast access, like in-memory data access to the most recent messages, right? Obviously, older messages, you have to go to the file system to pick up the data from the file, which basically means reading from disk. So that takes a bit longer. But if you just need real-time data exchange, if you need access to the most recent data, the most refreshed data, then the distributed architecture of Kafka allows for a wide set of memory resources to be pulled in together, and those recent messages are very likely to be actually in memory. So the kind of optimizations it does is, to make the operating system cache be responsible for actually storing the data in memory, and Kafka by itself actually just manages the consistency around making sure that the data is not lost and things like that. So this actually allows it to support a software architecture which relies on real-time message exchange and constantly refreshed data sets which need to be exchanged between, let's say, microservices. So if you find that the performance of Kafka is actually not very good, one of the first things you might want to do is, for instance, add more memory, right? Or add machines which actually provide more memory to the cluster. So that almost always actually solves a lot of the performance problems in practice. And that kind of an ease of understanding, that kind of an ease of architecture and performance tuning made it like really, really popular, right? One of the reasons why it became very popular. And the last thing that it did very, very well, I mean, again, these are just, unique things to Kafka. There are many more features, obviously. The last thing that it did very well was to consciously, from day one, say that, look, I'm going to prepare for eventualities of failures, because these are commodity machines I'm talking about, very similar to that Hadoop, origin story. So in preparing for failures, I really need to give a guarantee that the data is actually not going to be lost. So therefore, resilience is actually baked in from day one into the design of Kafka, such that there is always going to be, data sets available in other machines, even if the primary machine to fail. But even that was actually organized intelligently using, data partitioning. We'll talk about that. Okay, so before we go further, let's just take a look at how Kafka is used in the real world. So this was actually an architecture published by Myntra. It's a dated architecture in the sense that Myntra first published this almost 5-6 years ago in a public presentation, and maybe, if I could, even in a blog post, I believe. So in a sense, the entire Myntra architecture is fundamentally designed around massive scale event collection and processing, with Kafka as like the central backbone of that architecture. So in the front end, it's a mobile app. Myntra was for the longest of times just available on the mobile app, and even now mobile-based shopping at Myntra is actually the most popular channel, I believe. So when a user interacts with the Myntra app, right, there's a variety of different things that get captured as events, starting from as simple as mouse over, clicking on a specific link or a specific part of the mobile interface, etc. All of those are events, right? And all of those events are necessary, or I should say, are being collected to form more informed points of view about who the customer is and what their preferences are. So imagine the typical browsing experience on Myntra. For a particular page, you might be doing like you might be generating tens of events because of moving around, tapping around, etc., etc. Right? Or even the act of not doing anything or just looking at a particular dress or a particular page itself is actually an event, right? So it's fascinating how much you can glean about user behaviors just based on all of the data that the mobile collects, and that's what actually Myntra did. So those events are extremely voluminous, as you can imagine. They run into like billions, right, on a regular basis. So that data fundamentally has to be brought in. Obviously, it gets merged along with the some of the core data sets, like transactions, inventory, adding to the shopping cart, making a payments and stuff like that. So it's all interleaved. It's all event, right, in its most generic sense. So the entry point for that event data is what's called as a load balancer. The load balancer then splits those different entry point events into event collectors. The event collectors were written in a programming language called as Golang, and then that event collector, all it did was strip away certain parts of the data so that there is some level of routing that can be done, some level of decisioning, simple decisioning that can be done, and then it immediately writes into like appropriate Kafka topics based on what the event is a type of, right? So the notion of a topic in Kafka is very similar to the notion of a topic in PubSub. We'll take a look at those definitions in the next slide. But then all those events were routed into Kafka, right? So that became the central backbone for the event collection. So from there is a Spark job that read those events, and it followed what's called as the like Lambda architecture. So one aspect of that Spark job was batch processing. It would basically wake up every now and then and read events from Kafka of various topics, like topics which are of interest to the business would be things like transactions and payments and stuff like that. So those data sets, for instance, would get read in a batch form and then get updated in a data warehouse, right? A data warehouse is part of its OLAP infrastructure. And separately, there is a like a Spark streaming job which would run and do things like scoring, and that scoring would be responsible for things like personalization and stuff like that, right? And then separately, there was also a separate technology from Pinterest, the company Pinterest, again open source technology called Secor. What it did was allowed you to take Kafka topics, Kafka data, and drain into like a large storage area, right? So that you can keep adding all the data that you've collected over a period of time into a common place that serves as your data lake, like de facto data lake. So that was actually one of the other processing that happened. So 3 different types of consumers on that Kafka. Yeah. So in just to put again things into perspective, in some of those end of reason sale activities at Myntra, there used to be like more than I'm talking like 5-6 years ago, there used to be more than 20 million events happening on a daily basis. So that's the kind of data sets that were actually pumped into Kafka, and Kafka used to scale gracefully whenever that happened. In fact, I think Myntra went on record saying for the end of reason sale itself, this entire infrastructure was actually set up in a way that was dramatically bigger because they were obviously expecting volume. I mean, all major e-commerce companies do that, right? In preparation for a huge spike in volume, they scale up the infrastructure and be ready with it. And once it's done, once the sale period is done, they shrink the infrastructure back again. So, like for instance, the Kafka cluster hypothetically could have gone from like a 20 node cluster to a 10 node cluster after the event, right? And nothing changes about the technology, about the software, etc., right? So that's the beauty of having something that's fundamentally incrementally scalable. Okay, the core concepts of Kafka, first and foremost, is the message, and this should not be surprising. It's very similar to what PubSub does, right? So the message is the simplest unit of the payload, and obviously you can put anything in that, right? You can put binary data, ASCII data, etc. So very similar to PubSub. Topic is just like a feed of messages. Again, very similar to PubSub. Here, a topic is actually there are additional layers of I would say design that you need to think about, and we'll get to that in the next few slides. But yeah, at its base level, the topic here is very similar to a topic in PubSub in Google. Consumer is the entity that's the process that's actually reading the messages from the topic, and producer is actually the writing messages to Kafka topic. So again, nothing different. In Google PubSub, we spoke about this as a subscriber. Here it's called as a consumer. Then the Kafka cluster itself, because it's not a serverless system, it's actually an open source software. Obviously, you need to know what the internals are, right? Every node, every machine in the Kafka cluster is called as a broker. So the idea being, it actually has no point of view on what the messages are. It just allows the producers and consumers to exchange messages, and therefore it plays the role of a neutral broker, right? That's the origin of the term. So every node in the Kafka cluster is a broker. No node is a special node, right? Every node is equally special as the other, right? So in that sense, it's like a peer-to-peer architecture as opposed to like a master-slave kind of an architecture, or a master worker kind of an architecture like that Spark has or Hadoop has. Okay, so what is a topic? And here's where you have to really start digging into specifics of what Kafka is. And this is different from, let's say, for instance, PubSub or like RabbitMQ or one of those other technologies. So a topic is, like I said, a feed of messages, but it itself is actually partitioned. Partitioned meaning there's a group of messages that belong to that topic, which only exclusively reside in a specific partition, which doesn't have any other copy in any other partition, right? So likewise, there are other groups of such messages in other partitions. Together, all those partitions form the entire topic, right? So each partition stores a subset. And how does the partitions get created? They get created at the point of specification or creation of the topic. Usually, in practice, this is done at the point of design, right? So basically, the producer has to consciously work out what is the partitioning mechanism they want to use for their messages, and then that is aligned to the partitioning that the topic has been created with by Kafka, and then it rolls forward from there. Now, these partitions, the reason this partitioning concept came into play for topics is because you want to be able to have scalability innately built out. So if you didn't have partitions, if you just had a continuous feed of messages, which is what RabbitMQ, ZeroMQ were all doing, then you're effectively this rate at which you can read the messages is governed by the rate at which the server, the message server, can serve those messages to you. So if all of this is actually sitting in one partition or sitting without partitioning, basically in one machine, then that machine is going to become like the bottleneck in terms of the rate at which the messages can be consumed. So even if you have multiple different consumers operating at the same time, because the machine is singular in nature, then it actually becomes a bottleneck very quickly. So when the fundamental design of a topic was done, it was kept in mind that it actually had to scale across multiple machines and leverage the compute power, leverage the memory that multiple machines brought to the cluster. And therefore, the partitions were necessarily stored on different brokers, as many brokers as they were available in the cluster. So you could have a cluster of 3 brokers, and you could have your topic split across, let's say, 6 partitions, in which case 2 partitions of the topic reside in every broker. That way, you actually are able to fully leverage all of the brokers' combined capacity and get the scalability that was required, get the parallelization that was required. In fact, when the consumer consumes from the partition, they can actually in parallel read from all of these partitions at the same time. So that makes for a dramatic improvement in terms of throughput, in terms of scalability as well. So within a partition, right, the partition is like it's a first in first out queue. So there is a sequentially ordered nature to how the messages are stored within the partition, and because it's sequentially ordered, you can think about there being an offset compared to a specific point in the queue. So let's say, for instance, you start at the beginning of the queue. The offset allows you to say that messages, that particular message which has a particular offset number, is offset units separated from the head of the queue. The head of the queue is a starting point of the queue, right? So that allows it to keep growing by simply adding more messages and then having the offsets be incremented, right? So as long as the offset is continuously increasing, right, monotonically increasing, you can keep adding messages to a Kafka partition and not have to worry about scale or any other kind of maintenance, right? So within a partition, the messages are ordered sequentially, and that's something that Kafka actually ensures that it happens. So the producer will decide, right, which partition to write into based on, let's say, for instance, some kind of a hash partitioning scheme or some kind of a partitioning based on the key, or in other cases, it could just be a round robin system, which means it just writes every message to every new broker alternatively, right? So that all brokers are covered, all the partitions are covered, and then it starts again from the beginning, right? So that's a round robin mechanism. So whatever partitioning scheme the producer uses, Kafka ensures that all the messages to a particular partition, it's maintained sequentially in the way in which it was actually provided to Kafka at all in the first place. And that ordering, that message ordering guarantee is a crucial guarantee that allows the consumer to know that they can read the order. I mean, they can read the messages in the order in which it was produced, but within a partition, right? Across partitions, the ordering is not obeyed because these are, residing on potentially different machines, and I don't want to create sequential dependencies between them. I want to be able to parallelize my read. So across partitions, there is no guarantee, but within a partition, the messages are guaranteed to be in order in which it was produced and given to Kafka. Okay, so consumers, when they start reading messages from the queue, basically messages from a partition, they can firstly, of course, initialize the offset to begin at the beginning of the queue, but then at any point in time, they can set the offset to a specific number and read only the messages from that particular offset. So think of it like again, like a queue which allows you to just change the offset, which is a very simple operation, right? You don't need to actually go read the messages for that to happen. You can just simply change the offset, and that makes you that allows you to go to any point in that queue and read the data from there. And in fact, at any point in time, you can also change the offset back to an earlier point in the queue or to a later point in the queue. Doesn't matter. And there are very convenient mnemonics available. Like for instance, you can say that the offset should be at the latest point in the queue, which is like the most recent data, or it should be at the earliest point in the queue, etc. So those become, easy ways to reset and start again and things like that. So, like as you can imagine, this makes it very easy to reason about rewind and playback, right? We spoke about that in the context of the streaming problem statement in the previous week's lecture. Okay, so the other advantage of this offset kind of offset-based reading is that consumers could come and go. They could, like for instance, they could be failures and consumers could be offline for some time, and then they come back and say, look, I want to just continue from where I left off. So go back to that offset and give me the data. And multiple consumers could actually have their own offsets, right? Kafka doesn't care. So that makes it really, really simple from a modeling standpoint as to how you go about consuming the data. Okay, so in a nutshell then, if you want to uniquely identify a message, it's a combination of the topic, the partition, and the offset within that partition. So if you're given these three, you can uniquely identify a specific message, and that is a very, very powerful way to think about messages. And if you do this at scale, for instance, you can truly get to very large scale message consumption architectures, each having their own preferences, each having their own latencies, each having their own throughput characteristics, and none of that actually affects anything that happens at the producing side or anything that happens within the Kafka cluster itself. So there's actually immense power in this kind of a simplicity. Great. So I'll pause here for this video. Next video will continue with a deeper dive into Kafka. Thanks.